And what I illustrated you here, just looking by few examples of ambiguities in this very simple, though weird sentence, that in order to be able to interpret language, we need to have two things. We need to have knowledge about language, correct? We need to understand what is the meaning of the words, how do they fit together, how do they create meaning, and we also need to know something about the world. And it's the interaction of the two that help us interpretation. And what's interesting, people took two different approaches to this subject. One approach is symbolic approach. People thought, okay, the reason I understand something, I can actually kind of declaratively specify what is there in my head, what are the grammar, what is the relevant knowledge of the language, and then let machine reason in this very rich world. And this approach was kind of very common in old AI before statistical methods came in. Another approach is a statistical view, that you say, the world is complex, it's impossible for me to write down all the knowledge. I'm just going to give to machine what we call here, training instances of tasks that I care about, and then machines should be able to learn to perform my task. We're not making an assessment, we're not making a claim that machine really understand the whole natural language, but we're just saying we want a particular task to do, let's say, spam prediction. We're going to give a lot of instances of material related to spam, and it will learn it. It still doesn't understand language, but that's something useful. And it's very interesting that if you look historically, and many of you are thinking, what is the connection to linguistics? So the ideas of using statistical methods had roots even like in 50s, where the coders from Second World War were thinking about language as a coding system. But then comes this very famous article by Noam Chomsky, who was a professor in linguistics at MIT, who said that actually there is no way that machine can really deeply understand language. And his famous phrase that he used was colorless green ideas sleep furiously versus furiously sleep ideas green colorless. And he was saying both of the sentences would never appear in reality, but the first of the sentences is grammatical, the second one is not grammatical. So how we can actually, how machine can discriminate it if it never seen any? And we already know that in order for us to do an assessment, we don't actually have to see the whole sentence. We can build other tools that would enable us to discriminate between grammatical and ungrammatical sentences, even for utterances that we've never seen before. And in fact, you can very easily today, with today's machine learning, predict what is the right one. But this was a very impactful article, and it kind of, in some way, stopped research in machine learning approaches for NLP for a few decades. And then what happened, another person who relates to MIT, who is really an amazing figure in natural language processing, Frajelnik, who unfortunately passed away, who actually comes from statistical background, who was a student at MIT and who took classes with Noam Chomsky in linguistics. He was an information theorist, but he really cared about language. So at any rate, he was the first person who came to IBM and built a hidden Markov model for speech processing. This was the first time it actually demonstrated the statistical system doing something very useful, and his group pioneered the statistical machine translation, which kind of moved it from the realm of trip on Mars to something that can be used today. But he took it to a very extreme, saying whenever I fire a linguist, our system performance improves. So for a while, like in 90s, it was, in the early 90s, it was very, very, conflicted area, but now I should say we are all in peace. Just to illustrate you how people were thinking about it in 70s and 80s, there was a system developed at MIT called Strudel, and in AI lab. And what the system was doing, it was just moving blocks. So you can say, move the red block and put the green on top, and the machine, if there is some ambiguity, will say which green, big one or small one. Very elaborate things. And the funniest part is that actually even today, the level of language understanding that it required to do it, and to understand what is available, what is not available, how pieces carry it was really, really hard. It's still hard. And the way they solved it, they had like a very deep semantic model that kind of introduce the world, introduce what happens when you move piece in certain direction. So you have the full model of the world, and then natural language is done on top of this reasoning. But the problem was that you really need to encode by hand all of those relations. There was no learning. And people were very enthusiastic about it for a while and tried to have many domains, but then they realized you can do it for a small domain, but it would never scale up because you just can't code it. And I would tell you that on my personal example that, when I finished my master's thesis and I did it on summarization, it was such a different time that you didn't even have to put evaluation. You just show example of output, and this is an example of output from my first published paper, but there was no numbers. There was just an example of output. So the field really changed since then, and empirical revolution in the field actually happened in 90s. And the reason it happened was because Penn Tree Bank, which was a very important resource, was released in 93. So it was 1 million words from Wall Street Journal, which were annotated with sparse tree. So this is sparse tree. So the machine had a sentence and it had a corresponding sparse tree. So then we can start thinking about it as a training process, and we can think about solving it using the methods that we know from NLP. Then many people started really, who were more algorithmically oriented, started actually looking at this task and come up with many parsers. And just to illustrate you the difference between kind of statistical thinking and symbolic thinking, let's look at the task of determiner placement. For myself and for many other non-native speakers, placing determiner like or there or nothing is actually a non-trivial task, especially if your native language differently use determiner system or doesn't have them all together. And this is a piece of text which is unique because we removed all the determiners from this text. And what they do at MIT in the class actually ask students to put determiners back. And even among English native speakers, sometimes there is disagreement as to where this determiner should be. And you can say, why? Say, oh, it's very easy because we can, determiner placement is determine, the type of noun, whether it is countable or not countable, whether it is unique, we just have, the sun, not many suns, or at least not the big sun. Is it a new, we just introduce something to this course, or old, what is a number? So there are some kind of very clear rules. So why is it so hard? Because there are endless amount of exceptions and clarifications. This is one that I found actually in a big grammar textbook I have in my office. The definite article is used with a newspaper title, The Times, but zero article in names of magazines and journals, Time. So you can really see how much knowledge do we need to be able to make the determination. Also, there is some difference between like rivers and oceans. If you're interested, you can check it out. Really kind of bizarre set of rules. It's very hard to imagine that somebody would really remember all these rules when they move to a new language, and it's really hard to encode this information. So now let's think about it in a way which is the way we're thinking about this problem after this class. We can say we're given many texts, we have noun phrases. We can just identify what is a noun phrase, like for instance, lazy monkeys versus the United States. We can encode the question, is it plural, is it a first appearance? We can ask many feature type of question, and there are 2 types of feature questions that are available. And then we can just run our classifier. I drew you here a linear classifier, but you can be using any classifier you like, maybe something much more powerful because you have a lot of data. And they took your data, like people stopped working on this problem research-wise, but the best numbers at the time were 86% of insertion accuracy. I'm pretty sure that if you try now to do it with neural models, you can go much higher. And I'm sure it's better than what I will do when I do free writing. So this illustrates to you how you can take a problem which is really hard to explain directly with the linguistic knowledge and with world knowledge. You can cast it as very simple machine learning problem and get yourself a solution. And in fact, the reason I think it's much better now, because there are even commercial packages which you can buy and they will edit your grammar. So you can see that through machine learning perspective, it's really, really an easy task.